The James Webb Space Telescope may have discovered galaxies. That should not exist, and the terrifying possibility is that the telescope itself might be lying to us. This is the hidden engineering crisis behind the James Webb Space Telescope. Recent observations from the James Webb Space Telescope have identified galaxies so massive in the early universe that they appear to challenge our core cosmological models, sparking a crisis in astrophysics. A rigorous analysis of the instrument's own technical limitations and data processing pipelines, however, reveals a different story. The anomaly stems not from a flaw in our physics, but from the profound engineering challenge of interpreting individual photons, captured at the thermodynamic limit. This investigation will deconstruct how these impossible objects are statistical ghosts, born from the complex interplay of cosmic dust, redshift, and the unavoidable uncertainties of deep space observation. Since becoming operational, the James Webb Space Telescope has systematically identified a population of objects in the nascent universe that appear fundamentally inconsistent with established cosmological timelines. Initial data releases, particularly from deep field surveys, have revealed candidate galaxies at redshifts exceeding 10, a temporal marker corresponding to a period only 300 to 400 million years after the Big Bang. According to the prevailing lambda cold dark matter model of cosmology, this epoch should be characterized by small, proto-galactic structures in the early stages of hierarchical assembly. Instead, as reported in a flurry of papers submitted to outlets like the Astrophysical Journal, the JWST has found objects that not only appear to possess stellar masses, rivaling those of galaxies billions of years older, but also exhibit unexpectedly mature features. Develop disk structures, significant chemical enrichment. This observational evidence does not directly contradict the foundational concept of the Big Bang, the expansion of the universe from an initial hot, dense state, but it creates a significant tension with the predicted schedule of cosmic evolution. The standard model posits a gradual bottom-up process of formation, where massive, orderly galaxies are the end product of a long history of mergers and accretion. The existence of these impossible early galaxies, sometimes referred to as universe breakers in popular media, forces a critical scientific question. Are we witnessing a genuine failure of our most successful cosmological model? A paradigm shift in our understanding of galaxy formation? Or are we encountering a systematic observational bias, an illusion created by pushing our most advanced instrumentation to its absolute physical limits? The anomaly is therefore not a simple observation, but a profound fork in the road of inquiry. One path leads to new physics. The other leads to a deeper understanding of the intricate deceptions inherent in capturing ancient light. The core of this cosmological puzzle lies in candidate galaxies from the early universe that appear far too massive and far too mature for their supposed age. The genesis of these extraordinary claims lies not in a single, unambiguous discovery, but in the systematic application of a specific observational technique known as photometry. This method is the workhorse of deep sky surveys, allowing the James Webb Space Telescope to efficiently map vast patches of the sky and identify thousands of faint objects in a single exposure. In essence, photometry measures the brightness of an object, as seen through a series of distinct, wideband color filters, akin to capturing a scene using only a red, a green, and an infrared-sensitive plate from the relative brightness in each filter. Astronomers construct a color profile for a distant galaxy. That profile is then fed into computational models to produce a photometric redshift, or photos, a probabilistic estimate of its distance. This is a method of broad strokes and calculated inference, but it is fundamentally an educated guess, not a direct measurement, and it is fraught with potential for misinterpretation. The primary vulnerability of this technique is a problem of ambiguity known in astrophysics as degeneracy, a condition where two entirely different types of celestial objects, at different distances, can produce nearly identical color profiles. A primary example of this is the confusion between a genuinely high redshift galaxy whose light from young blue stars has been stretched to red and infrared wavelengths by cosmic expansion, and a galaxy at a much more moderate distance that is simply heavily enshrouded in dust. This dust absorbs blue light and re-radiates energy in the infrared, making the closer galaxy appear anomalously red, thus tricking the photometric analysis into assigning it a much greater and more impossible distance. This critical uncertainty means that many of the initial candidates for universe-breaking galaxies, as cataloged by data processing centers like the Space Telescope Science Institute, are subject to significant doubt. The definitive resolution to this ambiguity is spectroscopy, a far more meticulous and observationally demanding process. Using an instrument like the ESA Near-Infrared Spectrograph, or NIRSpec, astronomers can isolate the light from a single target galaxy and disperse it into a high-resolution spectrum, a detailed barcode of its chemical composition and velocity. This spectrum reveals the precise, characteristic emission or absorption lines of elements like hydrogen and oxygen, whose wavelengths are known from laboratory physics by measuring exactly how far these spectral lines have shifted toward the red end of the spectrum. A spectroscopic redshift is determined. This is not an estimate. It is a direct physical measurement of cosmic expansion's effect on that galaxy's light, providing an unequivocal confirmation of its distance and age. However, this certainty comes at a high operational cost. While photometry can catalog thousands of candidates in hours, acquiring a clean spectrum from a single unimaginably faint galaxy can require dedicating the JWST's focus for an entire day or more. This creates a severe data bottleneck. A flood of intriguing but unconfirmed photometric candidates far outpaces the slow, methodical trickle of spectroscopic verifications. The universe-breaking galaxies candidates are therefore predominantly identified through the fast, but highly uncertain method of photometric estimation, not yet confirmed by the definitive measurement of spectroscopy. At the heart of this observational conundrum are two distinct but interacting physical processes that systematically distort the light from the early universe, creating a cosmic mirage, perfectly tailored to deceive infrared instruments, like those on the JWST. The first of these is cosmological redshift, a direct consequence of the expansion of space itself. As photons journey across billions of light years from a distant galaxy to our telescope, the very fabric of space-time they traverse is stretching, and this expansion stretches the wavelength of the light along with it. The energetic, blue, and ultraviolet light characteristic of massive, young, hot stars, the very stars we expect to dominate the earliest galaxies, is shifted so profoundly over these vast distances that it arrives at our detectors as lower energy, longer wavelength infrared light. The James Webb Space Telescope was explicitly engineered to capture this faint, ancient signal, peering into the infrared spectrum, where the early universe's light now resides. This is not merely a reddening. It is a fundamental transformation of the information carried by the light. The second and more deceptive phenomenon is the effect of interstellar dust. Galaxies are not pristine collections of stars. They are permeated by vast clouds of silicate and carbon-based particles, the accumulated soot of previous generations of stellar evolution. This dust is remarkably effective at absorbing high-energy ultraviolet and visible starlight, particularly from the intensely luminous regions of new star formation. The energy absorbed by these dust grains heats them, causing them to glow and re-radiate that stolen energy at much longer, cooler infrared wavelengths. This physical process, extensively modeled by institutions like the Harvard-Smithsonian Center for Astrophysics, means that a galaxy undergoing a vigorous burst of star formation can be almost entirely invisible in optical light, but blaze brightly in the infrared. The critical issue arises because this dust-induced reddening can create an infrared color profile that is nearly indistinguishable from the color profile produced by cosmological redshift. These two processes converge to create a profound observational ambiguity. When the JWST sensors detect a faint, extremely red object, they are capturing a signal with two plausible origins. It could be the signature of a genuinely ancient, high-redshift galaxy whose light has been stretched for over 13 billion years, confirming the presence of a surprisingly massive structure in the cosmic dawn. Or the signal could originate from a significantly younger, less distant, and less massive galaxy that is simply choked with dust from an intense, localized starburst. In this latter scenario, the object's extreme redness is not a measure of immense distance and age, but a sign of intense, obscured activity. Differentiating between these two possibilities, using only the broad-brush data from photometry, is an immense challenge. The computational models must make critical assumptions about the unknown dust content and temperature within the target galaxy. An incorrect assumption can lead directly to the conclusion that a dusty compact galaxy is a colossal, ancient leviathan. Interstellar dust can absorb the blue light from young stars and remit it as infrared radiation, making a galaxy appear significantly redder and thus deceptively older and more massive than it truly is. Underpinning the entire capability of the James Webb Space Telescope is an unprecedented feat of thermal engineering. The instrument's very ability to perceive the faint infrared universe is predicated on being colder than the signals it seeks to detect. Any object with a temperature above absolute zero radiates energy, and for a telescope designed to see the faint warmth of the first galaxies, its own structure, mirrors, detectors, and supports, is a potential source of blinding thermal noise. Consequently, seeing the distant cosmos is not an act of simple photography, but of thermodynamic warfare against the instrument's own self-emission. This battle is most extreme for the mid-infrared instrument, or MIRI, which is designed to capture the longest and most redshifted wavelengths. According to engineering specifications from partners like the NASA Goddard Space Flight Center, MIRI must be actively cooled to an operating temperature below 7 Kelvin, a mere 7 degrees above absolute zero, or minus 266 degrees Celsius. Achieving and maintaining this temperature in the vacuum of space represents a hard physical floor set by the laws of thermodynamics, beyond which lies a fog of intrinsic detector noise, from which no signal can be recovered. At these extreme faintness levels, observation ceases to be analogous to taking a photograph and becomes an exercise in statistical photon counting. The light from a candidate galaxy 13 billion light-years away is not a steady stream, but a sparse rain of individual photons arriving at the detector, only a few at a time, over many hours of dedicated observation. The resulting raw data is not a crisp image, but a complex dataset, where the faint celestial signal is buried within the inherent noise of the electronics and the residual thermal background. The process of extracting a detection from this data, a task managed by sophisticated software pipelines at the Space Telescope Science Institute, involves meticulously modeling and subtracting all known sources of noise to determine whether a statistically significant excess of photons remains at a specific location. Therefore, what is presented as an impossible galaxy is not a direct, unambiguous portrait. It is a probabilistic confirmation that a signal exists above the noise threshold, a faint peak in a vast field of statistical uncertainty. This fundamental reality of the measurement process means that every claim about the mass, age, or structure of these objects is an interpretation built upon a signal so tenuous that it pushes the physical laws governing our sensors to their ultimate limit. The JWST extreme sensitivity is achieved by operating its mid-infrared instrument at under 7 Kelvin, transforming observations of the earliest galaxies from clear pictures into statistical detections of individual photons. The purported cosmic crisis sparked by the James Webb Space Telescope is therefore not a failure of physics, but a testament to the profound difficulty of interpreting a universe observed at the absolute limits of temperature and light. These statistical ghosts, born from the ambiguities of photometric data and the deceptive glow of cosmic dust, are less a challenge to our cosmological models and more a reflection of the inherent uncertainty when our finest engineering confronts the faintest signals from the dawn of time. The anomaly ultimately reveals not a broken universe, but the precise boundary where observation becomes interpretation. If this deep dive into the engineering behind the headlines is the kind of analysis you value, because at the edge of the observable universe, every photon carries a story, and on this channel, we follow those stories to the limits of physics itself. Subscribe to Tech Dissect Official for more deep investigations. At the edge of science and engineering, and the limits of human observation, we'd like to leave you with a question for the comments. What do you believe is the greater challenge for modern astrophysics? Building ever more powerful instruments, or developing the sophisticated methods required to interpret the faint, noisy data they produce? Thank you for joining us for this analysis, and we'll see you in the next one. Next, we investigate the silent heat crisis threatening to halt Moore's law and explore the radical new architectures designed to compute beyond the limits of silicon.